All right, so welcome to day 2 of, what is this, Mathematical Statistics 377, Operations Research. Just checking as it's 9 a.m. Okay, so what I want to do is before we get into actual math today, I want to just talk a little bit about some of the possible projects. So the first is working with some healthcare providers in the Berkshires on some medical issues. I really can't go into too much detail with a live mic right now. There will be a lunch meeting tomorrow sometime between 11 and 1. The time will be whatever works best with the majority of people who are coming, who've expressed interest in coming. So if you are interested in that, please send me an email, even during class is fine, just so I have an idea of what time works best. Other possible projects is working with the new owners of the Lanesboro Mall to try to keep the mall viable in the era of Amazon and online shopping. Another one is a project for a Major League franchise. I can't get into, again, too much detail with the camera rolling, but if you're interested in something like that, let me know. There'll be some scheduling problems for a variety of organizations, including the elementary school. There's going to be a couple of other projects that pop up as time goes on. If any of these strike your fancy, if you want to just learn a little bit more of them, please let me know. Okay, so we ended with almost nothing mathematical in the first day. It was basically the mechanics. We at least did one small bit of math so you could see something. What was the last bit of mathematics we did? Babylonian Mathematics. So we basically ended a couple thousand years ago mathematically. Okay? Not bad for the first day. If you consider the universe is billions of years old, we're within a couple thousand years of modern mathematics. That's not bad. What is really good from the Babylonian Mathematics? What was the key takeaway? Yes? I'm sorry, you only have to know squares. So what does this allow us to create? Lookup tables. So that's one of the most fundamental ideas we have, is can you pre-compute some calculations and save the results? So a lot of times in theoretical math classes, it doesn't really matter. You just need a bound exists, a real analysis. We have a lot of wonderful theorems. If you have a finite closed interval and you have a continuous function, it attains a maximum, it attains a minimum. We may not know where, we may not know what that value is, but we know the existence. And a lot of times just the notion of the existence is enough for the conversations we need. Frequently, however, we actually want to know where is the maximum, how would we find it? Typically, we can't find it exactly. If you take a good algebra class, you learn that eventually, if your polynomial is of degree 5 or higher, there's no closed form solution for the roots in terms of the coefficients. And we have to resort to numerical approximations. How closely can we get the root? How quickly will we get to the root? So these are huge concepts. And we want to get a sense of what the answer is to a certain level of tolerance. So frequently what you do is you have a bunch of calculations that you do ahead of time, and you use those to interpolate values in between. And for many purposes, that's good enough. And so then the question becomes, how do you choose the values that you compute? Do you choose them equally spaced? Probably not. How many of you have taken a differential equation? Differential equations class, sorry, not differential equation. Okay, excellent. So have you seen numerical methods to solve differential equations? Maybe like the Euler method? And when you do the Euler method, do you do equispaced jumps? You keep moving down by size of h. It's frequently better not to move by the same step block every single time. If you only have a certain amount of time you can compute, you might want to do more computations where the first derivative is large and the function is changing rapidly, and fewer computations where the first derivative is relatively small in absolute value. Dynamic computations. So these are extremely powerful ideas. The other thing before I forget is you should see a red light on me, green light on me, and a green light on the machine. If either of those green lights die and you're the first to let me know, you will get extra credit. Because that means one of the things is no longer paired or recording. Okay? So what I want to do now is I want to revisit math you've seen with an eye to efficiency. So revisiting old math for efficiency. Okay, so I'm going to start off with something you've probably seen a long time ago in algebra class, evaluating polynomials. This is not a hard subject. If I give you f of x is 14x cubed minus 7x plus 21, and I want to know what f of 2 is, how would I find f of 2? Plug it in, great. So we're now just a little bit above where my son is in elementary school. Excellent. We're making remarkable progress. We've moved a couple thousand years already. This is not that bad if the polynomial is small. But what you always want to be thinking about is what happens as the polynomial gets larger and larger and larger. So more generally, let's consider f of x is an x to the n plus an minus 1 x to the n minus 1 plus a1x plus a0. So we have a polynomial now. And the question becomes, if we want to calculate this at 2, well, we can again just replace all the x's with 2, and we'll get an times 2 to the n plus an minus 1, 2 to the n minus 1, plus yada, 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 a1 times 2 plus a0. So let's see how many multiplications does each piece cost. How many multiplications does it cost to get this piece? N. We have n minus 1 to get 2 to the n, and then one more to get the an. This piece is going to cost us n minus 1 all the way down to 0. So we have, for multiplications, it's going to be n plus n minus 1 all the way down to 0. And how many additions do we have? Yeah, it's either n or n minus 1, something like that, right? Because we're going down to a0, so you have to figure it out. For me, the easiest thing is, well, if I take n equals 1, I see there's one addition, so there should be n additions with n. Which do you think is more expensive, typically, multiplication or addition? Multiplication. Think of two 20-digit numbers. Think of all the cross multiplications you need to do versus just the number of additions you need to do. So if you look in terms of the cost in terms of the number of digits, multiplication is far more expensive than addition. So really, the n additions, you can almost throw them in for free. The relative cost of the n additions is so small, it's all being dominated by the n multiplications. And then the n minus 1 multiplication, then the n minus 2, et cetera, et cetera, et cetera. So the question is, what is the total cost? Let's say the total multiplication cost. So we want to sum 0 plus 1 plus 2 plus n. So this is an extremely famous sum. Goes all the way back to, I think the earliest story you hear about this is Gauss. He had a teacher who was having a bad day and wanted to shut the little brats up. So the teacher thought, let me give them a long sum to do, and it'll take them a while to do it, and I can just have some rest. And so the story goes, the teacher asked them to sum from 0 to 100. Or maybe 1 to 100, it doesn't really matter. Expecting to have a couple of minutes respite, and then Gauss raises his hand and immediately says the answer. How can you solve this so quickly? Yes?
You do it in pairs, starting with the first one.
Good. So one thing is to do this in pairs. If we call this sum s, then if we write it backwards, n plus n minus 1 plus 0 is also equal to s. So we get twice s, and each pair now is going to be n. And how many pairs do we have? You all agree we have n plus 1 pairs? So we have n plus 1 times n is twice s. Therefore, s is n plus 1 over 2, which is approximately n squared over 2. So if you want to just get a sense of how bad the calculation is, it's roughly on the order of n squared, or a little bit better, 1/2 n squared. One of the things that I'm really big on is approximation. We really do not need to approximate this sum that well. And the reason is because we have a closed form expression for it. We can evaluate it very easily. If I were to make the sum more complicated, however, it would be a very different story. That's why I want to spend a little time right now talking about how would you approximate this sum. I know we're approximating a sum we can evaluate exactly. It's to show a good order of magnitude estimate. So let's try to find upper and lower bounds. So I'm going to erase this, just try to stay in a better area of the blackboard. So let's estimate. So the sum is 0 plus 1 plus n. And you can decide whether or not you want to keep the 0. Let's drop the 0 so we have n terms. All right. Can somebody give me a really bad lower bound?
Oh, that lower bound?
Yes. You want to give the upper bound?
Yeah, I might do
Okay, give me a really bad lower bound.
bad lower bound is, I would say, n.
Good. That's a very bad lower bound. And can you give me a bad upper bound?
Well, we can see that every term in the sequence is upper bounded by n.
Good.
And give a really bad upper bound is n times n squared.
Excellent. So this tells us the true answer is somewhere between n and n squared. Unfortunately, the powers of these numbers are not the same, so we don't have the right order of magnitude. But we know it's at least growing as fast as linear, and it's not growing faster than quadratic. Can anybody, which bound do you think we want to improve, the lower bound or the upper bound? Yes.
The upper bound.
And?
What?
And? Yeah, we want to improve both.
Oh, yeah.
Right? Which do you think is the more crucial one to improve, the upper bound or the lower bound? And remember, we have additional information. We know what the sum equals. The lower bound is the more important one, because the lower bound is the one that's further from the truth. So can anybody give me a good way to improve the lower bound? To get something maybe of size n squared, up to some constant multiple. Yes?
You break the sum into two halves, so the first half is from 1 to n over 2.
Good.
And it is from n over 2 to
Good, so we break the sum into halves, and the second half going from n over 2, technically the second half, it's like n over 2 with the floor plus 1 all the way up to n. This is extremely painful to write things like the floor function and remember the plus 1, right? So to make our lives a little bit easier, what might we want to just assume about n as we're doing the analysis?
Even?
It's even. So if we assume n is even, I don't have to worry about the floor function. Or I could subtract 1, and then I'd be fine. Because if I subtract 1, the worst case scenario is if this is almost, if this is like integer 0.999999999, when I have the floor function, I lose the 0.9999999. I'll check later in the video to see if I had the right number of 9s. And then if I just subtract 1, that's going to easily compensate for the floor function. Or the other thing is to say, look, it's like this. If my life depended on it, I would do the analysis a little bit more carefully. But for all practical purposes, for lower bound, I have n over 2 terms, where each term is at least n over 2. And by doing that, now we know the true answer is somewhere between n squared over 4 and n squared. So the true answer is n squared over 2, approximately. This is not bad. A really quick, simple argument gave us the correct order of magnitude. Then the question is, can we do a better job? And there's lots of tricks you can play. I'm not going to really go into them right now. Of course, the best one is, as in the proof, was pairing things and writing the sum backwards. But what I like is we can get a good sense of the order of magnitude cost by just very quickly looking at, what the sums are, really bad, crude bounds. Does anybody have a good way to improve the upper bound? So we improve the lower bound to n squared over 4. Can we lower the upper bound? So I claim we already have enough on the board to lower the upper bound.
I suppose we could break it in halves again.
Yeah, break it in halves again. Well, use the same break.
Yeah, use the same break.
Use the same break. So in the first half, every term is at most n over 2. So we'd have n over 2 terms of size n over 2. And in the second, each term we have n over 2 terms of size n. So now we would get 1/4 n squared is at most s is, now we have 1/4 plus 1/2, I think is 3/4. And in fact, the average of those two numbers is the correct order of magnitude. It's also interesting to see how much work is required improving the different bounds. What would it take us to do even better? What if we broke this up into fourths? How good would that be? What if we broke it up into eighths? What do you think the natural question is? And we'll assume n is a perfect power of 2. What's the limit as you keep getting? Should this converge to being n squared over 2? So it's a nice extra credit problem. Assume n is going to infinity through powers of 2 and keep breaking things in half. So if n equals 2 to the k, break it up into k or k minus 1 times. Keep breaking up, keep breaking up, keep breaking up. Can you make this argument precise, and can you get n squared over 2? This is, of course, ridiculous overkill. Right? This is a horrible, horrible, horrible way to prove n squared over 2. We have much better ways. We have writing the sum backwards. We have proofs by induction. This is one of the standard problems you do in proofs by induction. But it's interesting to just see how far can you push the method, and it's a great way to review some of your real analysis, some of your limiting arguments. Okay, any questions on estimating the cost? Okay, so we know the cost is on the order of n squared. So this is going to be a huge theme for the class. So I'm going to write over here, cost is approximately n squared over 2 multiplications. So if I go from a polynomial of degree n to a polynomial of degree 2n, I increase n by a factor of 4. I increase the runtime by a factor of 4. If I increase n by a factor of 10, I increase the runtime by a factor of 100. You want to get a sense of how long is it going to take an algorithm to run. For some of the stuff I've done for real-world applications, if every subatomic particle in the universe was a supercomputer devoted exclusively to my use, running since the dawn of time, I would not have enough computing power to make a dent in the problem. For other things I've done, I need just a little bit more computing power than I have available. And so you really want to get a sense of how difficult is the calculation. Do you expect to be able to do it? As it's growing, will you be able to do it, or will it quickly be beyond what you can do? So the first question is there a better way to evaluate this polynomial? And I'm going to do initially a generic polynomial. It should not be surprising that if my polynomial has additional structure, there will be better ways to evaluate it than evaluating a general polynomial. This is a very common theme. Right? The more structure something has, the more tricks you can have tailored to what's going on. And what you frequently want to do is you want to break something up into maybe like a structured part and maybe like a fluctuation part and try to control something like this. But right now, let's assume that we do not have anything structured. So what I'm going to do is I'm going to do Horner's algorithm. I'm not going to do a rigorous, detailed proof of why it works. I'm going to prove by example. This is, of course, not a valid way of proving things, but it's enough to give you the method. And if you want to make it rigorous, it's a good exercise. So how many of you have heard of Horner's algorithm? Okay. Absolutely beautiful idea. In terms of theoretical mathematics, how important is Horner's algorithm? Not at all. Do we need a new way to evaluate polynomials theoretically? No. We just need patience. Or grad students. Right? Now, if we want to get something done in real time, if we want to do something in the world, brute force evaluation is horrible. Horner's algorithm is wonderful. So let's take f of x equals 23x to the 21 plus 14x to the 20 minus 7x to the 19 plus dot, 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 dot. And I'm going to just show you how you would evaluate this using Horner's algorithm. So this is going to be on the order of n squared over 2 multiplications if we do it naively. Here's the fast way. It's by grouping. It's 23x plus 14 times x minus 7 times x plus dot, dot, dot. And you just keep marching down like that. And what you'll see is as we keep going down, we keep incrementing the power of x by 1. So at the end of the day, we'll get 23x to the 21. This has one smaller power of x. So at the end of the day, this will give us 14x to the 20. This has two smaller, so we'll get negative 7x to the 19. All we've done is we've grouped things. So let's look at the cost. How many multiplications does this require? N. You may be off by 1. I think you're right, but it's on the order of n multiplications. How many additions? N. Again, you might be off by 1. I'm just saying this because it's being recorded. I don't really care if we're off by 1. I care about the n dependence. A small little constant flip is not a problem. This now, the cost, oh, this is n multiplications. Cost is n multiplications. We don't care about additions. So if you compare this to what we had before, the addition cost hasn't changed, and the multiplication cost has gone down by a square root, essentially. This is a remarkable increase in efficiency. You can do far more with something like this than you can with something else, with the brute force approximation. Let's think about it. Do you think you should be able to evaluate a polynomial of degree n in fewer than n multiplications? Depends on the structure. Great way to keep yourself safe. If I give you a generic, no, always put in something like that to protect yourself. If I give you a generic polynomial, so this polynomial has no special properties, do you think that there is a clever way to evaluate it in fewer than n multiplications? So there's a lot of things in cryptography where we believe it's hard. Why do we believe it's hard? Smart people have tried for a long time and haven't solved it. What's the problem with this?
Doesn't mean it's unsolvable.
Yeah, it does not mean. It just means no one has found a solution yet, or there's something else it could mean. No one has published a solution. Years ago, I was fortunate enough to take a class in mathematics on number theory from someone from the NSA. It was a very enjoyable class, but frequently when we would ask questions to the instructor, he would say, I'm not allowed to comment. But what? No. I am not allowed to say anything other than I am not allowed to comment, because if I say anything else, that could give you information about what I may or may not know. There's a lot of things in mathematics and number theory that is used for encryption. A lot of these are built on problems that appear to be hard unless you know a special piece of information, a backdoor key. This doesn't mean that that's the only way to quickly solve the number. Factorization is a great example. We don't know publicly a good way to factor a large number quickly. We know a good way to tell if a number is prime, but we don't know a good way to find the prime factors. There may be a good way that the NASA or other organizations know about but haven't told us. I have heard stories that there are mathematicians who've had results published, and then once these are published, the NSA or other organizations at a certain time say, go to the following mailbox in Wichita, Kansas, or something like that, and you will find a sealed envelope stamped by a notary of the public, from 20 years ago, with the solution that we wanted to protect the priority of one of our workers, but we did not want people to know that we had solved this. You've got to be very careful about this, because if it comes out that the NSA has had something for 20 years, then all of a sudden you go, oh, the NSA might have known about what we've been doing for 20 years, and they've been acting accordingly. So you've got to be extremely careful about what information you give away. So it does not seem like there's a faster way of evaluating this polynomial than going brute force through everything. And it seems like we have to do at least n multiplications. We've got n terms. Horner's algorithm seems to be essentially the best you could hope for. Whether or not it is another story. Can you prove that there's nothing better for a generic polynomial? Let's look at a special polynomial now. If you could choose any polynomial to evaluate, what is the simplest polynomial that you think I'll let you get away with evaluating? F of x equals x. So it's a very good specific polynomial, not going to be too hard. I want at least some parameter with n for things to get larger. So x to the n, right? This is a special type of polynomial. We could apply Horner's algorithm to this. By Horner, this is x times x times x times x dot 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 dot. So if we use Horner's algorithm, how many multiplications? So the number of multiplications is n minus 1. So the question is, can we do better than n minus 1 multiplications? And this is a very special polynomial. So the hope is maybe we can do better for this one polynomial. All right, any thoughts as to how we could do better? Yes?
We can split up n.
Okay, how could we split up n?
For example, if that's like x to the fourth, then you can just do x squared, and you can store
Excellent. So this is called fast multiplication. So the idea is to use the binary expansion. And binary is very nice. Computers love binary. So I'm going to give a proof by using an example. And I always use 100. So if n equals 100, if I want to write that in base 2, that's 64 plus 32 plus 4. OK? So now I can write x to the 100 as x to the 64, x to the 32, x to the 4th. And I just have to find those terms. X times x is x squared. X squared times x squared is x to the 4th. X to the 4th times x to the 4th is x to the 8th. X to the 8th, x to the 8th is x to the 16th. This is right where I always remember why I hate choosing a number like 100, but at least it's deep enough to see what's going on. X to the 16 times x to the 16 is x to the 32, and x to the 32 times x to the 32 is x to the 64. So let's count how many multiplications. 1, 2, 3, 4, 5, 6. That gets us to there. 7, 8. So 8 multiplications versus 99. Now, when you only have one data point, it might not be clear what's going on. Is this approximately square root savings? Because 8 squared is 64, which is approximately 99. So maybe it's a square root savings. Or maybe it's a 1/10 savings, because 8 is about 1/10 of 99. It's actually much better than all of those. Approximately how many multiplications is it going to cost? Log n. So if you take a number theory class, and I will be teaching one in the spring, what base do we do for logarithms in number theory? E. Theoretical mathematicians, we love base E. E is wonderful. In the practical world, E has issues. Okay? What are the natural bases? Well, no, that's a horrible word to use, sorry. What are the good bases to use for real-world computations? 2. And there's another choice. 10. All right? Why do we like base 10? Okay, 10 fingers. The universe probably does not care that we have 10 fingers. I cannot prove that to you, but probably doesn't care that we have 10 fingers. 2 is very nice. On, off, yes, no. True, false. Power on, power off. Computers love working in base 2s and stuff like that. For some things, disk data storage, base 3 is better than base 2. I won't go into it now. If people are interested, I'll go into it later. There's a really nice number that lives between 2 and 3. What number am I thinking of? E. Here's the halfway mark between 2 and 3. E is closer to 3 than it is to 2. And because of that, base 3 is actually more efficient for storage of information than base 2. The most efficient base is base E, which we really can't work with practically. So if people are interested, I might say a few things about that. So the real question is, how many steps does it take? It's at most 2 log base 2 of n multiplications. When doing fast multiplication. And the reason is we have to figure out what's the highest power of 2 that could come in the expansion. So if we want to write n as 2 to the k plus dot, 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 dot. What's the largest k could be? K is at most the log of n base 2. So in terms of when I do the base 2 expansion of n, the highest term I could have is the log of n base 2. And then the worst possibility is if my number n is 1 less than a power of 2. So worst case, n is 2 to the L minus 1. And that's going to force me to have as many multiplications as possible and as many combining at the end of the day. So it's a good exercise to just go through, finish the calculation, and show that the worst possible cost is essentially 2 log of n base 2. I may be able to subtract 1 from this. I don't really care if I can subtract 1 from this. I care about the growth rate within. Okay? Any questions on what we've done up till now? Theoretically, does this matter? No. Okay? Theoretically, this does not matter. We already have a way to calculate x to the n. From a practical perspective, if it wasn't for this, you wouldn't be able to do a lot of online shopping. Or at least you wouldn't be able to do it securely. When you do encryption, it's not enough to encode and decode the messages. You need to be able to do it in a reasonable amount of time. You're probably way too young for this, but how many of you remember? Or have seen some old movies? I think You've Got Mail is a classic, with the dial-up sounds, and just how long it would take to establish the connection and to send the information. And it's very frustrating. I hope my parents don't watch this part, but it was always hard going from college, where we had really good internet connections, back home to the dial-up, and just how much longer everything took. Right? Streaming video. Do you remember when streaming video was choppy and had a lot of issues loading? How is it now? I think right now it's pretty good. I mean, you look at how many videos you can watch online and stream. You've got to send the information back and forth very fast. All of these things, it's not enough to be able to do it. You need to do it well. You need to do it quickly. This fast multiplication, this is the basis of why RSA, which is one of the most common gold standards of encryption, runs quickly and is thus usable. You have to calculate things to powers of the size 10 to the 200. Okay, if we do brute force and we take n to be 10 to the 200, good luck. Anybody know roughly how many subatomic particles there are in the universe? Roughly. Within 10 orders of magnitude.
10 to 80?
Yeah, I think it's around 10 to the 88, something like that. Let's round up. Let's say there's 10 to the 100 subatomic particles in the universe. Make each one of them a supercomputer devoted exclusively to you, doing 10 to the 20th computations per second, well beyond what our supercomputers can do. That gets you on the order of 10 to the 120 computations per second. Look at how many seconds the universe has existed. It's less than 10 to the 40. That gets you up to 10 to the 160. We're raising a number to the 10 to the 200th power in RSA encryption typically. This gives you a sense of how monstrous those brute force computations are. But if we now do things on the logarithm, well, what's the log of 10 to the 200? It's roughly 200 log 10. Log 10 is about 2.3. So we're talking about 230. I can do 230 computations. Well, actually, I can't, but my computer could. That is manageable. That's the power of something like this, the incredible savings of going from an order n to an order log n algorithm. And this will be very important when we start doing things like linear programming, when we get to the search space that's just too big to exhaustively look at. Probably on Wednesday's class, I'll talk a little bit about fractals. When I was in, I think, high school, I wrote a program in Pascal, that's how old I am, to generate fractal images. And brute force polynomial evaluation was too slow for my computer to do the necessary computations. I actually had to implement Horner's algorithm. It was still slow, but it could at least display it in a reasonable amount of time. All right, so this is fast multiplication. This is great. You know, we're now at least in the 20th century of mathematics. We're getting closer. So let's go back to one of the prereqs. Let's go to linear algebra. So one of the big problems in linear algebra is I give you two matrices A and B. I want to compute the matrix product AB. For certain classes of matrices, this is not a hard calculation. Usually there's some smartass who will give me a really easy B. One is the diagonal matrix. You can be a little bit more of a smartass than that. Identity matrix, right? Zero matrix, any multiple of the identity matrix. These would be really nice ones. How do we calculate A times B in general? Well, let's look. Let's say we have A and B are n by n matrices. So n by n, n by n. How do we calculate the entries of C, this product? Okay, so row by row. So we take a row here, and we take a column here, and we do the dot product. So if this is the ith row, and this is the bth column, is it confusing if I'm using A's and B's for rows and columns, that one is a column, one is a row? Is that okay? People don't seem to be complaining. And then the ijth entry would be AI dotted with bj. Okay. We have an algorithm to multiply matrices. In case this wasn't emphasized in your linear algebra class, there's a lot of different ways of looking at a matrix. One of the best ways of looking at a matrix is a transformation written in a given basis. And depending on what problem you're looking at, you want to choose a different basis. Okay? So I might talk a little bit about that later in the semester as to how we go about finding the right basis for a problem. And if you find the right basis, the problem becomes significantly easier. Theoretically, we have an algorithm. And think of this as we have the transformation B, which we then follow with the transformation A. That's the same as some new transformation C. And the entries of C are given as follows. How many entries does C have? Yes, n squared. So C has n squared entries. How many multiplications does it take to determine a given entry of C? Yes, n. Each requires, oh, that's a hobble written, requires n multiplications. So the total cost is what? N cubed. Okay, so n cubed multiplications, good or bad? Okay, I see a thumbs down. This is bad. Why is this so bad?
When it gets big, it gets real simple.
Yes, we will easily have matrices of size 10,000 by 10,000, potentially more. Now, sometimes these matrices are sparse. Sparse means mostly zeros. We have algorithms that deal with sparse matrices, where you don't have to save those things because most products are zero. But we are not in that case. We're considering the general case of multiplying two matrices. This is going to cost us on the order of n cubed. So if we double the size of the matrix, the algorithm will run 8 times slower. One of the greatest advances in 20th century mathematics was lowering the 3. And after a lot of work, there was a new algorithm. It replaces the 3 with the log of 7 base 2. Can anybody find a number that's really close to the log of 7 base 2? E. 3. Right? What's 3? Yeah, 3 is just the log of 8 base 2. So foreshadowing, the art of a prepared professor. Okay? So I have written down 7 products. Do not ask where these products came from. But they're here. So as long as they're here, let's look at them. Okay? How many multiplications does each of these products take? 1. And then I've written C11, is that sum? C21, is this sum? C12, is this sum? C22, is this sum? No more multiplications. So the cost is 7 multiplications. And let's count additions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Maybe, if I haven't made a mistake, maybe 18 additions. When we looked at what we did before, if we had 2 by 2 matrices, 2 by 2 matrices, how many multiplications would that cost? 8 multiplications. And how many additions? 4. Because we have 4 entries. Each entry with the dot product is going to be a sum of 2 terms. So this is the first time where it's not an obvious comparison. When we were doing Horner, we basically had the same number of additions but fewer multiplications. This is a no-brainer, right? Here, there's a trade. at the cost of doing 14 more additions, I can do one fewer multiplication. Is that a good deal? Yes. Turns out this is a great deal. And the whole point is 8 is the log of 2, is the log. If we take the log of 8 base 2, we get 3. If we take the log of 7 base 2, we get the log of 7 base 2, which is a little bit less than 3. What this allows us to do is this allows us to come up with a way of multiplying matrices that's not order n cubed. It's order n to a smaller power. And you can do a little bit better than the log of 7 base 2, but this is the simplest one to write. Now, of course, most of the matrices you're going to look at are not 2 by 2. If they're 2 by 2, maybe this isn't really worth it. But if we have a really large matrix, like a 4 by 4 matrix, what we can do is we can break the 4 by 4 matrix into 2 by 2 chunks. And then we do this in each 2 by 2 chunk. And after 4 by 4 matrix, what would you like to look at next? An 8 by 8, a 16 by 16. So what this is telling you is that when you're doing a lot of these calculations, you want to have your matrix dimension a power of 2. It makes these algorithms a lot easier to look at. So frequently when you're doing these numerical calculations, if you have to choose maybe how many data points you want or whatever, you will choose things to be a power of 2 to set things up perfectly for this. If you don't have things nicely as a power of 2, what might you do? So your matrix maybe is 15 by 15. Crap. What should you do? Yeah, add zeros. Pad up the matrix. So if your matrix is 15 by 15, put a couple more zeros in to make it a 16 by 16 matrix, and then use this algorithm. So what's the best choice of B? Well, of course, diagonal matrix, identity matrix, multiple of the identity, these are all nice. If B equals a power of A, this is fast multiplication. This is what we were just doing earlier today. So if you want to compute a high power of a matrix, we have a great way of doing that. So it all ties together. And it is amazing how much lowering this exponent helps calculations in the real world. By going down from 3 to the log of 7 base 2, it makes a lot of algorithms much more applicable for real world problems. The runtime has been lowered to the point where we can use them. So one of the big things I want you to get out of this course is whenever you see things, can you find a faster way of doing it? Frequently, sadly, it's not going to be that much of a difference. It's not going to really make a huge deal one way or the other if you're looking at small cookbook problems that we give you in class. But when you go into the real world and you have extremely large data sets, any small savings here gets magnified. And it can come down to how many times can you run your simulation? How big of a set can you analyze? One of the best quotes I've heard, and I may have already said this, is when I was a postdoc at Ohio State, I was in a data analysis seminar. And one of the speakers said, every day we have more information beamed down by the weather satellites than is in the Library of Congress. And we've got a couple of hours to analyze it for our weather prediction models. This would have been probably about 14 years ago. And so I can only imagine how much data we're getting now. You have to find efficient ways to sift through all of this. Okay, so any questions on Horner's algorithm? I should actually give a name to this. This is called Strasson's algorithm. So this is Strasson's algorithm. Is there a way to get a Strasson's algorithm for 3 by 3 matrices? Is there a way to do a Strasson's algorithm for 4 by 4 matrices other than breaking it into 2 by 2 blocks? How did you come up with, or how did Strasson or someone come up with this collection? If you guess that there's a form like this, are there ways to figure it out? Has anybody here taken algebraic number theory? Okay. Did you have to look at the discriminant of polynomials, like the discriminant of a cubic? Was that a very painful calculation?
Yeah.
Did you see the fast way by looking at special cubics? So I apologize that this is now directed for 2 people, but there's something called the discriminant of a polynomial. And it turns out that if I give you a polynomial x cubed plus ax squared plus bx plus c, you can associate a discriminant. Without loss of generality, you can assume the quadratic term vanishes. And then it's got to be a certain polynomial in the coefficients. You even know what the degrees of each product is. You then look at special terms. You look at x cubed minus 1 or x cubed minus x. And you figure out what the discriminant is in those cases. And that allows you to then figure out what it is in general by looking at some special cases if you have an idea of what the functional form is. If you assume that you have forms like this, is it possible to figure out what these expressions must be? Could you write a computer program and search through the space and figure it out? So for instance, it's not that hard to figure it out when I write it on the blackboard. But what if I said, look, you have a bunch of products. Each product involving the A's has either 1 or 2 terms. Each product involving the B's has 1 or 2 terms. And there's a way to combine them. Is that enough information for you to write a computer program and sniff this out? Does that computer program have to be efficient? No. How often are you using that computer program? Once. So if you're only doing something once, you can often be inefficient and just try to sniff out what the answer is. I'll give you a nice challenge. Nice coding problem. And this will probably be a good place to stop. So I'm going to give you the numbers 1 through 9. And I'm going to form 3 numbers, A over BC plus D over EF plus G over HI. And this is not a product. What BC means is 10 times B plus C. There is a way to put the numbers 1 through 9 in the slots A through I, such that this sum equals 1. So I was at a math institute a couple of years ago, and someone brought up this problem. And so I'm surrounded by a bunch of the top number theorists in the world. And you know what they start doing? They start proving theorems about what some of these numbers must be. You know what I do? I write a computer program in Mathematica to loop over all the 9 factorial permutations. I save myself a little bit of time because I can do some structural things. I write a very bad program. It takes me maybe 3 or 4 minutes to write the program because I'm not trying to write the program really well. I only have to run the program once. The program's not the most efficient. But by the time I run my program and I get the result, they're still proving things about where the 5 must be located or something like that. I admit that they're understanding the problem at a much deeper level than I am, but I got the answer first. So this is a really good point to remember. So this class is going to be different than most of your standard math classes. I really want to spend a lot of time emphasizing stories, emphasizing ways to look at things. There's going to be fewer standard statement proof theorems as you would get in another math class. There's going to be guest speakers. There's going to be projects. If this is not something you like, this is a great time to realize that. But I really want to try to teach you some of the skills and perspectives that will help you when you leave Williams. I will be around in my office for some of today at various times.